Okay, hello. Finishing up from class on Thursday, we ended with the grand conclusion being the matrix basis theorem, which enables us to write a 2x2 matrix to perform any kind of transformation that we want by simply looking at what that matrix does to 1, 0, and 0, 1. So we have seen rotations by 90 degrees, rotations by 180 degrees, reflections across the x-axis, y-axis, and line y equals x. We've seen some dilations, and we have seen some, shears. Okay, here's one that's extremely important. Suppose you want to rotate points by theta degrees counterclockwise. Okay, so already, immediately more or less, we should say, okay, I want to figure out the matrix that will do this. Well, I don't know what my matrix is at the moment, so I need to answer basically two questions. What does this matrix do to 1, 0? And I'm going to figure that out here. And what does this matrix do to 0, 1? It's the same logic that we use over and over again. And then whatever we find are the answers to these two questions. This matrix, this vector is going to be column 1 of my matrix M, and this vector will be column 2 of my matrix M. Alright, so this whole thing just reduces to this kind of geometry problem. What happens when you rotate the vector 1, 0 by theta degrees? So this suggests we need to make some kind of picture. And okay, here is the picture. And yeah, trigonometry is involved. So what have I done here? I've sort of drawn a unit circle. Why? Because my original vector, well, I guess I'll just do it in black here. My original vector is the vector 1, 0. So there it is, the vector 1, 0. And well, basically, you know, what happens when you rotate this point by theta degrees? Well, you just get this point over here. Alright, we know exactly what happens when you take a vector of length 1 and rotate it by theta degrees. You end up with a certain point on the unit circle. And in fact, just by definition, this point on the unit circle is cosine theta comma sine theta. In other words, the first part of this question answers itself very quickly. This is my, perhaps I should have used, here, just working on my color scheme a little bit here. This was my original vector. In purple, I will draw my transformed vector, the vector after having rotated. Okay, that's just cosine theta sine theta. So actually, that's just the answer, right? This matrix should take the vector 1, 0 and send it to cosine theta sine theta. Cosine theta and sine theta just outputs the x-coordinate and the y-coordinate, respectively, of the point on the unit circle, which has been rotated by theta degrees. Just to add a little bit more detail to this picture, if you kind of drop this perpendicular down, well, this green is sine theta, and hopefully that's a little bit legible on the camera, and this red is cosine theta. Okay, cool. Well, that was pretty easy. How about the other one? What happens when I rotate the vector 0, 1 by theta degrees counterclockwise? Well, it helps if you've chosen a theta that looks like about, 20 or 30 or something like that. Enough to be acute and small enough that it doesn't look like 45. And okay, so I was here. Sorry, I lost my convention again. I was here at the point 0, 1, and then I rotated by theta degrees. And if I rotate by theta degrees, I end up with this purple vector. And what do I have to say about this purple vector? Well, it's sort of theta degrees. This was theta degrees from the x-axis, and this was sort of theta degrees from the y-axis. Okay, and then the casual way to finish this off is to just figure out what the coordinates of that point are using kind of just common sense. And the common sense way to do it would be to just kind of use geometry and triangles and to say, well, these two triangles are congruent, of course, and so this green here is sine theta, the length of it is, and this red here is cosine theta. And so, if you take the point 0, 1 and rotate it theta degrees, it's simply a fact of geometry that you end up with this point here, which is in fact, it has x coordinate negative sine theta and y coordinate cosine theta. And that is the answer. If you sort of are skeptical of this or don't like your proofs to be like kind of via picture, there's another way to do this. It's a little bit more formal, which is that you know, this point right here, after all, is a point on the unit circle. So can't we use the definition of the trig functions? Yeah, we can. What is this sort of big angle here? Well, this big blue obtuse angle is in fact just 90 plus theta. And so by the definition of the trig functions, that point actually has coordinates. Well, every point has coordinates, you know, cosine comma sine, but this time it's cosine of theta plus 90, and it's sine of theta plus 90. Okay, and now if you just like apply some trig identities, you know, what is cosine of theta plus 90? Well, it's cosine theta cosine 90, but cosine 90 is 0, minus sine theta sine 90, but sine 90 is 1. And so you just get, by kind of cranking out the formula for what happens, well, there are other ways to do this, but that's one way. What is sine of theta plus 90? Well, it's sine cosine, so it's sine theta cosine 90, but again cosine 90 is 0, plus sine cosine theta sine 90, but again sine 90 is 1. Okay, so if you sort of don't trust the picture, this is the alternative way to derive the coordinates of that point over there. But I think this is sort of more beautiful. Okay, what is the conclusion of all of this? The conclusion of all of this is that the matrix M that I want is the matrix whose first column is cosine theta sine theta, and whose second column is negative sine theta cosine theta. And this is just kind of cool because what this means is that, you know, give me some vector. Well, let's just take our vector 5, 2. Right? Take our vector 5, 2. Suppose I wanna rotate it, you know, by 20 degrees counterclockwise or something like that, and I have a calculator, say, then I just kind of dial up this matrix, you know, cosine 20 degrees, I don't feel like writing degrees, sine 20 degrees, negative sine 20 degrees, and cosine 20 degrees, and then I can just input this vector 5, 2 into that matrix, and whatever I get back again will be exactly what happens to that point, to that vector 5, 2 as it gets rotated 20 degrees. Okay, so this is nice if you want to sort of program or whatever some points to get rotated. This is the fastest way to do it, I think. Okay, good. There's one more thing to do. That was kind of the important stuff. There's sort of one more application of this same topic, which I think is interesting and which sort of brings a lot of stuff together. Sometimes you don't have a geometric description of the transformation. Sometimes you only know what the transformation does to certain points. So suppose suppose I want a matrix that does the following. here's the description of this matrix. It sends the point A, which has coordinates 4, 5, to A prime with coordinates 14, 17, and it also sends this point B, which is 2, 1, to B prime, which is 4, 7. Okay, can you find me the matrix which does that particular transformation? Well, let's call this matrix X. Call this matrix X. Okay, and I guess the way now to sort of translate this into language that we find easier to work with is, there's some matrix X. What does it do? Well, here's what I know that it does. When you feed it the vector 4, 5, it outputs the vector 14, 17. And the other thing that this matrix X does is if you feed it the vector 2, 1, it outputs the vector 4, 7. Okay, but this is what I call sort of the slow way, or something like that. The way of sort of combining this together. Well, maybe I'll just do it here. I'll just do it here. So the conclusion of all of this is that, in fact, what this matrix does is it sort of eats two vectors and gives back another pair of vectors. So this is just another way of writing the same thing, that if you feed this matrix X 4, 5, then what you get back is 14, 17, and if you feed it 2, 1, then what you get back is 4, 7. So in other words, I need a matrix which eats these two vectors and spits back these two vectors. Okay, well, you can think of this is now just kind of a matrix equation, right? I don't know, so I don't know kind of what this matrix is. So I'm sort of going to now write this as like A, B, C, D. This is my kind of unknown matrix. I'm calling it matrix X, and I want to multiply it by this matrix 4, 5, 2, 1, which I'll call A, and I want to get back this matrix 14, 17, 4, 7. Let's call this matrix B. In other words, I've sort of converted this problem of finding the transformational matrix to this kind of matrix equation, X times A equals B. Alright, and how do I solve this matrix equation, X times A equals B? Alright, well, we need to be kind of careful. And I warned you earlier in the unit that we would have to be kind of careful. There's only one thing that we can do to this matrix equation, which is going to lead us to what we want. What we want is to solve for this matrix X, to get matrix X kind of by itself. Well, here I have to multiply by A inverse, but this time I need to right apply by A inverse. So unlike the other time when we left applied, this time we need to right apply. And you can see that that's correct by just imagining down into the sort of low level what is actually needed to get this matrix X by itself. The thing to do, the reason why multiplying by A inverse works is because I can now sort of reassociate here on the left hand side, and since A inverse is in fact just the identity matrix, then this is why X is just BA inverse. Alright, so that's totally clear, I think, but note that if you did it wrong, this time you wouldn't catch yourself, because since A is a 2 by 2 matrix, A inverse will also be a 2 by 2 matrix, and B is also a 2 by 2 matrix, of course. So I can multiply BA inverse, but I can also multiply A inverse B, and both of them will go through. BA inverse in this case is the correct answer, but A inverse B will be wrong. And in general, since matrix multiplication is not commutative, you'll get a different answer, which will be a wrong answer. So it really is true that you don't have to show all these steps every time, but you at least have to imagine yourself multiplying by A inverse on both sides on the right to eliminate that A that's there. And so since that's why the A inverse ends up there. Okay, so how do we just do the problem or whatever? Well, I just need to calculate the inverse of A. So okay, well let's just do it. What is the inverse of A? Well, it's going to be 1 over the determinant. So 4, 5, 2, 1, times the matrix that results from those two numbers swapping. So that's 1, 4, and those two numbers get negative. So it's -2, -5. Okay, so what is that? It's 4 minus 10, so it's -6. So this whole thing becomes -1/6 and times this matrix. Okay, so if that's, yep, looking good. So what is x? X will be B times A inverse. So I'm going to have my matrix B, 14, 17, 4, 7. That's my matrix B times this matrix here. And okay, the -1/6, we can just kind of leave that coefficient floating out there. That's probably the easiest thing to do. I sort of ran out of room a little bit here. Well, I guess I'll just go on to the next line. -1/6, and now I just have to perform this matrix multiplication. I think I can do this in my head. So row 1, column 1, so it's 14 minus 20, so it's -6. Row 1, column 2, so it's -28 and 16 is -12. 17 and minus 35, so it's -18. And finally, row 2, column 2, that's -34 and 28 is -6. Is that right? Yeah, that looks good. And now when I distribute the -1/6 through, I end up with 1, 2, 3, 1. Okay, so these were sort of nice numbers, and you get this kind of happy matrix, 1, 2, 3, 1. And well, the claim, if you wanted to check this, you could just take this matrix, 1, 3, 2, 1, plug in the vector 4, 5, and see what you get. Take the matrix 1, 3, 2, 1, plug in the vector 2, 1, and see what you get. Let's see if this is the matrix that does what it's supposed to do. Well, indeed, we get 14, 17, and here we get 4, I think, and 7. Is that what's supposed to happen? Yep. So there you go. Okay, I think this is the superior way to do it because it's kind of nice and helps us practice some of the things we learned earlier in the unit. In the book I gave you well, in the PDF that I'm about to send you with the homework problems for this topic, they don't do it this way. They take this, they have you, and you can do this also, it's fine, it's not wrong. They take this and they just multiply it all out, right? So they get 4a plus 5b equals 14, if I did that right. 4a plus 5b equals 14, And it's also true that 2a plus b equals 4. 2a plus b equals 4 when I multiply row 1 by column 2, and 2a plus... And so I now can solve this system of equations and figure out what A and B are, and then do it again with the C and D. You can do it that way, there's nothing wrong with that, but it seems inefficient to do all that when I already have the matrix equation, so why don't I just kind of go for it by solving that matrix equation since I know how to do that. Okay, goodbye.